Hello, my dear students. In radio engineering, we have to know some of the other parts like antenna and propagation. We have discussed in the previous lectures, but now there are some advanced theories that related to microwave engineering, and microwave engineering is a part of radio engineering. So that is the transmission line, or the we know that the waveguide and transmission line are the heart of microwave engineering because they are the propagation channels of microwave engineering. So for this, and we know that satellite communication is also related to this. So in radio communication, we have to have a knowledge on transmission line too. So what is transmission line? A transmission line is a connector which transmits energy from one point to another, and it has a distributed parameter network. So it's a parallel lines, two lines, which has capacitive and inductive properties, and we can then use the lumped circuit representation to understand this. First of all, we have to understand that there is a two-wire voltage and current definitions, equivalent circuit with incremental length of transmission line. It is a two-wire conductor line and distributed parameter network. And TEM, transverse electromagnetic propagation, is the propagation criteria of transmission line. Now, that is the types of transmission lines. There are basically four types of transmission lines. First of all, two-wire parallel transmission line that you can see here. Second is the coaxial lines that you can see here. There is will be outer insulation, then a copper mesh inside, then the insulation comes, and then we get the copper wire. And then the strip type substrate strip type substrate transmission lines, like that. Microstrip antennas are like that, and some waveguides just like this, rectangular waveguide, circular waveguide. So both waveguides are there. Now there are the transmission line parameters and Lambda model. What is Lambda model? First of all, we have discussed about the distributed model. So Lambda model, we will equivalent the two wires as the properties of electricity, that's resistance, inductance and capacitance, and also conductance. So we have used the four properties here. So for these properties, there we find out there is a series connection between resistance and inductance, and there is a parallel connection between conductance and capacitance. So here the resistance is the series resistance per unit length. Both are in unit length, so it is known as the Lambda model or distributed parameter, because del z, a very small amount of z propagation has been taken into account. Okay, and L is the series inductance per unit length for both conductors, and G is the shunt conductance, that means it is in parallel. C is the shunt capacitance per unit length, and G is Siemens to meter, Siemens by meter, and C is farad per meter. So in the next slide we will understand about the transmission line equations. So these equations are known as telegrapher's equations. It is written in the time domain form, as you can see that zt, that means both the parameter z and the time parameter t has been calculated in this section. And third is the Kirchhoff's voltage law and current law is used to derive this equation. To use to derive this equation, we have to use Kirchhoff's voltage law and current law. In what sense? First of all, we have to use in this node Kirchhoff's current law. So for this, if we use Kirchhoff's current law, so there are certain laws I, Z, T. We will be the inner what you can say, the input current, and both has been divided into three categories, three parts: I, Z, T, G, delta V, Z, V, and C is the C delta V, Z, and minus I, Z plus del Z comma T. That means they have been shift. And then in the voltage divider law, there is a V, that is V Z comma T minus R Z I and L Z, and minus V Z plus del Z T. So that is the transmission line equation. So first of all we have to derive from this equation. We have to adjust the KVL into that loop, and also find the you can say Kirchhoff's current law in that particular point. Then we can find this current. One goes through to the conductance, and other goes through the capacitance, and other is the output current. After finding that, we have to derive these two equations. Then we get the derivation of the two equations like that: minus RZIT IZT minus L DIZT divided by dt, and di dzt is equal to minus G VZT and C dVdt ZT. So that's the four final equations, and these equations are known as transmission line equations. Then we go through to the characteristic impedance. If a uniform lossless transmission line is considered for a wave traveling in one direction, the ratio of the amplitudes of voltage and current along that line, uh, which has no reflection, is called as characteristic impedance. That is the characteristics impedance. That means R naught equal to root over L by C. And here you can see that the characteristic impedance Z naught is the voltage wave value divided by the current wave value, root over. So there are two branches. First of all is the parallel one, that is the G plus J omega C, and the series one is the R plus J omega L. So these two values should have to be divided with root over part. And if it is a lossless line, it is denoted by Z naught, so we have to consider L and C is equal to 0. Then we get the lossless line R naught is equal to root over L by C. Sorry, R and G will be 0. I'm extremely sorry, apologies to me, that is R, apologies for me, that's R 0, R and G 0. The conductance and resistance, if it is 0, so it is considered as lossless line. Next we will go through to the impedance matching section. To achieve maximum power, we know in maximum power transfer theorem, we achieve maximum power transfer of the load, impedance matching has to be done. That means the Thevenin resistance should be equal to the load resistance. Here the resistance of the load should be equal to that the source and load should have to be equal in that particular impedance matching. The reactance of the load should be equal to that of the source, but opposite in sign. Reactance should have to be equal. That means if it is inductance XL, so that would be minus XS into the inductive side. If the source is inductive, the load should be capacitive, and vice versa. It's like this. If the load is inductive, that is XL, the load should be XC, that means capacitive. If it is capacitive, then it could be inductive, like that. The reactance of the load should be equal to that, but opposite in sign. So that is the impedance matching section. After that, we will go to the reflection coefficient, the parameter that expresses the amount of reflected energy due to impedance mismatch. That means the ratio of reflected voltage to the incident voltage is known as a reflection coefficient in that particular section. It is denoted by rho. And if the impedance between the derived and the transmission line don't match with each other, then the energy gets reflected. The higher the energy gets reflected, the greater will be the value of rho reflection coefficient. Now you can find out the voltage standing wave ratio, VSWR. The ratio of maximum voltage to the minimum voltage in a standing wave can be defined as voltage standing wave ratio, VSWR, maximum divided by minimum. And for their relationship with rho, that means the reflection coefficient, we find out is equal to 1 plus rho divided by 1 minus rho. So if the impedance is matched correctly, so the V maximum and V minimum will be equal, and that will be 1:1. The value of VSWR is unity, which means transmission is perfect. That means no reflection will be occurred. The efficiency of transmission lines. The efficiency of transmission line is defined as the ratio of the output power to the input power. As you can see, power delivered at the reception divided by the power sent from the transmission end, 100%. That is the efficiency of transmission line. Thank you very much for the last lecture of the radio engineering for being with me. I hope your every success in life.